till now we have seen the time temperature transformation diagram, the TTT diagram for eutectoid steels. Now, let us look at how this diagram, how the TTT diagram will vary if we consider hypoeutectoid or hypereutectoid steel. Recall that in the steel phase diagram, in the iron carbon phase diagram, this 0.8 weight percent carbon steel was the eutectoid steel, and this is what we have been considering till now. Any alloy with composition less than 0.8 weight percent is considered to be hypoeutectoid steel. So, let me take a composition. So, let me take this composition. Suppose we take a composition less than 0.8. So, that composition is represented by this vertical. So, my alloy composition C naught is less than 0.8. C naught is less than the eutectoid composition C e, which is 0.8 weight percent carbon. So, for this composition, that equilibrium transformation happens at the eutectoid temperature and also at this temperature where gamma starts transforming to alpha. So, as we cool along this line, in the single phase gamma will enter into alpha plus gamma, which means alpha starts precipitating, and you have seen that we call this alpha the pro-eutectoid alpha. So, corresponding to this in the and these temperatures in steel literature, quite often these I have been calling this the eutectoid temperature and labeling this as TE. Conventional labeling A1 is also used for this temperature, and similarly where the composition vertical hits this gamma alpha plus gamma boundary, that boundary temperature is known as A3. So, now you can see that there are two critical temperatures A1 and A3 for this alloy. So, this will reflect in the TTT diagram also. So, on the right I am going to draw the TTT diagram, and I am now transferring these temperatures onto the TTT diagram. So, this is going to be the TTT diagram for hypoeutectoid steel. So, there is a horizontal line corresponding to A3 and there is a horizontal line corresponding to A1, and of course, lower down, just like for eutectoid steel, you will have a horizontal line for MS, martensite start, and MF, the martensite finish. And then you have the C curves for the transformation, and just like for the eutectoid steel, you have two C curves for start and finish to alpha plus Fe3C formation. So, this is alpha plus Fe3C region, and you know we have seen that above the nose we get perlite. So, I write that perlite, both are alpha plus Fe3C, but microstructure are different, and below the nose we get bainite. Similarly, between the start and finish we have austenite plus perlite and austenite plus bainite. But stable austenite, in this you can see single phase stable austenite will be available only above A3. So, we have there stable austenite, and below A1 of course austenite is unstable. So, we have unstable austenite. I am writing austenite A, or you can write gamma also. I have used gamma here. Now you should be familiar with both these symbols. And however, as you can see that since proeutectoid alpha can form independently of Fe3C between A1 and A3, a corresponding line of the TTT diagram is required to represent this transformation, and that line starts from the nose of the C curve and goes asymptotically to the A3 temperature. So, this is, we can call this alpha start, proeutectoid alpha. So, this is an alpha start curve, and the phase in here between this line and this line is austenite plus alpha, the proeutectoid alpha, and the proeutectoid alpha will continue here. So, we will modify this with austenite plus proeutectoid alpha plus perlite, and the final microstructure also you will get perlite plus proeutectoid alpha. So, this is how the diagram gets modified. You can see that in the modified diagram there is no extension of the proeutectoid alpha line below the nose. So, if I quench a steel, hypoeutectoid steel below the nose and hold it isothermally, I will only get bainite, I will not get any proeutectoid alpha. But if I quench and hold above the nose, then initial transformation will be to proeutectoid alpha, and then further perlite will form. Now, exactly similar situation is there for hypereutectoid steel. Hypereutectoid steel, you should note, are steel with composition greater than. So, C naught is greater than 0.8, the eutectoid composition. So, the composition vertical is on the right hand side of 0.8, and there the phase is gamma plus Fe3C. So, the proeutectoid phase which you form is cementite. Just like we had called this boundary, the temperature corresponding to this boundary A3, in steel literature, the temperatures corresponding to this boundary are known as ACM. So, I have two critical temperature, A1 which is independent of composition, and ACM which will depend on composition. So, I transfer this on the temperature axis of the TTT diagram. So, I have A1 here and ACM here, and I have the two corresponding horizontal line. Again you have horizontal lines for MS and MF as well, and you have the start and finish line for perlite and bainite, but at the same time you have a line representing the start of proeutectoid cementite. So, this is pro Fe3C start. This goes it starts with the nose and goes asymptotically to the ACM temperature. So, if we write the phases, we have stable austenite, then we have here austenite plus cementite, here we will have austenite plus pro Fe3C plus perlite, and finally we will have pro Fe3C plus perlite. But just like in the hypoeutectoid case, if you quench below the nose, there is no formation of proeutectoid Fe3C, it is totally suppressed and you will get only bainite. there will be no proeutectoid Fe3C. This obviously is gamma plus martensite and this is martensite. So, this is how the diagram changes for hypoeutectoid and hypereutectoid steels.